It's actually given by me about what we are doing at SoftServe in terms of digital twinning and simulation for space robotics. Um, yeah, simulation first. That's like the approach that we advocate, and because we think in space robotics there's no room for error because of visibility of missions and so on and so forth. And we work a lot with the Nvidia Omniverse because SoftServe, as a service company that we are, we do not do products, but we deploy technologies developed by others, including Nvidia. We can have an advisory role for clients, but then also we can transition to the implementation side of things. And we are active across various industries, not just space. Actually, space is at this time still a rather small activity in the company. And whatever we do in space, we base that on Nvidia Omniverse, on Isaac Sim, and the various extensions and SDKs that come with the Omniverse. DJ Bush is here, for instance, of Nvidia, and who's been supporting us, let's say, on the client side and business generation. I don't know how many of you are familiar with the Omniverse, but it's a very potent ecosystem, and it's really tailor-made for robotics. So the vision is physical AI, agentic AI, to be able to digital twin complex robots, including sensor simulation, environment simulation, actuator simulation, for everything to come together. And we can likewise use it for space-related use cases. Yeah, we've been getting a couple of awards with regards to the NVIDIA collaboration. And again, most of what we do is non-space. But why do we think that in space we need smarter systems? Smarter systems meaning more autonomy. Well, because we in the space field, let's say we're looking at a couple of trends. For instance, where Earth orbital spaceflight is concerned, multi-satellite constellations are concerned, on-orbit servicing, mutual inspection, security related is a big topic, for instance. It's part of a space situational awareness. And in those scenarios, you may have disrupted communications, also large signal latency. So that's arguing for more local autonomy in the space segment. In planetary robotics, and a hot topic basically is more autonomy for sampling acquisition, sample handling, and if you think of ISRU, you want to have autonomous systems for local excavation of soil and in situ processing. So there are various drivers for increased and enhanced autonomy in space robotic systems. Also, the price cannot be ignored, the price pressure, let's say, on space robotic systems, because so far manipulators for space or rovers have not been exactly cheap. So any novel approach to lower the cost is also very welcome for these robotic systems. So what are the global themes for in-space technologies? And these have been inspiring us in the company because we've been focusing at SoftServe on certain use cases in space robotics. So Earth observation with various satellites and different frequency bands, multispectral, hyperspectral radar is something that's defining some of our projects. Think of edge processing on satellites. So we're working on some solutions there with partners, plus image post-processing or data post-processing on the ground. Connectivity and communications, this also comes down to control of large satellite constellations, prediction of space debris, conjunctions or object conjunctions in Earth orbit. So that can be a data intensive task and real-time demanding. Space robotics, yes, in the orbital domain around the Earth, it's about on-orbit servicing, plus inspection of other assets in free space and orbits, and lunar and surface robotics, including also XR for teleoperations, if you think of lunar robotics. And we've been focusing for the past 2 years really on lunar systems on the simulation side of things, including some XR extended reality aspects that we also tackle in the company. So imagine robots on the moon, be it humanoids, be more conventional ones. They will have some local autonomy. They will have onboard decision making, but still you want to be able to pass to them high-level commands, and that can be done through extended reality from space stations or from the Earth's surface, where you have a signal latency going to the moon of a couple seconds, and that allows you to do predictive control of such robots using digital twins of the robotic systems. Yes, and in our approach to simulation for space robotics and digital twinning for space robotics, we are guided by, let's say, in talking to customers, in talking to clients, the aerospace giants or startups that are active in space, they talk to us and they come to us with, let's say, their pains. I mean, this can be related to production, shop floor issues, and we are active anyways in production, assisting systems, including robotics on Earth, in Earth-based industries, and we can take that on to production of spacecraft and launchers and assist customers there. Digital twinning is important for virtual commissioning to lower the risk during development of space robotic systems. But also think of foundation models or digital twinning, even of geological formations, where resource distributions are concerned, on the moon, on asteroids, on Mars. And again, we let ourselves be guided by these use cases and pains. And so I will show you a couple of examples of our recent activities in simulation for space robotic systems. Obviously, simulation is not a domain per se, but it's needed, as also Dan has been pointing out in the first talk this morning. It's needed to support the design of robotic systems, to de-risk the development of such systems. That's how we see simulation. So simulation first, and also the digital twinning that has been our focus for space so far has been the simulation twin. We classify digital twins according to this logic, by the way. And a favorite example of mine, let's say, is our lunar drone concept. Well, drone meaning in this case, since we have no air on the moon, it's a thruster-propelled vehicle. It's just a vision, it's a concept of something that hopefully will become reality in a few years. It's driven by the need to improve prospecting for space resources. For instance, rovers on the surface, typically they move quite slowly. It's difficult. You can have treacherous terrain, immobilization, and then lunar orbiters, lunar satellites, considering resource prospecting on the moon. Lunar satellites, they move at a certain speed over ground, which makes it difficult to acquire high signal to noise data. Because of the speed over ground, which is relatively high. So we are thinking of this concept here, working on this with partners, where you would have a thruster-driven vehicle that can cover ground kilometers over several minutes or less, all the while looking downwards with remote sensing instruments, acquiring data. You can control lateral velocity while you're acquiring high signal to noise observations over shaded terrains at the lunar poles. So you can actually do quite sensitive measurements. So what we did do at SoftServe on this subject is model such a vehicle, hypothetical vehicle, including the onboard control system and autonomy. So we did all that in Isaac Sim. We modeled the sensors, two monocular cameras and an IMU, which in combination allow us to do visual SLAM for autonomous flight control. Point clouds are generated, and we looked at a scenario where this vehicle would fly through lunar lava tubes, which is one way of exploring such features on the moon. They do exist, and in our artificial lunar terrain that we built in support of the simulation, we considered these lava tubes based on actual, let's say, scientific observations of lunar orbital missions. And the surface terrain model of the for the moon that we used in the lunar drone simulation, we used an Nvidia replicator for changing various characteristics of the terrain, like rock distribution, slopes, crater distribution, and that's very helpful also in synthetic data generation for training robotic behaviors. Let's look at we have some movie of a flight going through a lunar lava tube. So this would be taken from, this is the camera perspective off of the lunar drone as it flies through the lava tube, autonomously finding its way in and out. Obviously, such a vehicle would be limited in flight duration because it's burning propellant, rocket propellant, and once you're done, then you would just crash. So the idea would be to acquire remote sensing data and come back out of the lava tube and land on the ground and then be refueled, so land on the surface. Yeah, it's quite let's say spectacular watching these movies coming out of the simulation, and we hope that in a few years from now, such systems will become reality. And lunar simulations, similar to what Dan and his team in Wisconsin are doing with Project Chrono, we are using, in this case, we are using Isaac Sim again in a co-simulation approach to look at ground vehicle mobility, interaction with the terrain, lunar roving systems, Mars roving systems, also excavation we looked at, because excavation is going to become important for resource extraction, ISRU on the moon and on other objects. So our co-simulation architecture makes use of the Isaac Sim physics engine. Plus, we work with FMUs, FMIs to describe the forces in between the asset, between the robotic system, so rover or excavating scoop, and the terrain and the soil. And we coded the terra mechanics equations, up to now just semi-empirical classical Becker-Wong equations, but as part of the overall co-simulation stack. And we defined like a robotic arm with a scoop and a vibration actuator to reduce the forces during excavation. So we tied all that together in the model with the terra mechanics and kind of ran the simulation. Plus, so this is the shadow of the robotic arm. Okay, this is the representation of a granular soil with which would be excavated by the scoop. And in the system, we have like a multispectral camera and we're looking at the simulated view from the camera system, which could be used to autonomously identify icy particles in the excavated material. So we kind of added icy particles into the model of the terrain and had the autonomy and image interpretation algorithm of the imager identify particles during the excavation. So just to demonstrate what is possible. And this approach we took forward in a an STTR contract for NASA that we are doing that will run for another year, which is related to preparing lunar terrain for landing and launch pads for large spacecraft. We're working with partners there, and we're simulating ground vehicles as part of that architecture, again with Terra Mechanics, and again with the co-simulation approach, like for the excavation simulation. It's the same principle where we have the interaction model between the wheel and the terrain, again, through an FMU architecture that talks to the simulation engine, which is PhysX in this case. And the model of the asset, so of the ground vehicle, is parametric. So we're able to vary geometrical parameters of that rover and be able to run the simulations for a large number of variations. And to finish off, I was going to show you the multi-robot on the moon, which is a combination of different robotic aspects for the moon for resource prospecting. So it's a lunar drone and its ground vehicles for excavation and processors as part of a lunar outpost architecture. So we have a little movie, again, coming out of a simulation. So where the drone would be deployed to do remote sensing measurements of the terrain, identifying targets of interest for excavation, and the ground vehicles would move up and excavate material. These are structures related to a lunar outpost. So imagine excavating icy soil and then transferring it to processors as part of the lunar outpost. And all of these multiple robots would be controlled by a central orchestrator that we modeled as part of the simulation. And such scenarios in analogous fashion can be used in industries on Earth, can be used in mining, orchestration of multiple vehicles in autonomous mining operations, for instance. All right, I was going to close it there. And we will, yeah, I'm happy to take a question right now. Otherwise, we'll transition to the panel format with the speakers of this morning.